First, I would like to clarify something about setting clocks on pulse signal in LT-SPICE. So, if we're going to operate the buck, we have two switches, S1 and S2. And then we have the decoupling cap, the load resistor, R, C, and L. And to drive these switches S1 and S2, we need pulse signal, or which is essentially a clock signal in LT-SPICE. Pulse 1 and pulse 2. In the pulse command in LT-SPICE, you specify V1, which is essentially the minimum value for the signal. It's going to be 0. So V1 should be 0 or V initial. And then V2 is basically whatever on voltage, say 5 volt. TD is the delay time. So the signal delay time, does it start at 0 or at a delayed fraction? So in this case, if we are setting S1, let's set it to have 0 nanosecond delay. And after that, we have the on time. If we are setting the on time for the pulse signal that's driving switch S1, it should be the duty cycle time, the cycle time T, right? Assume the duty cycle is 0.5. So we should set the on time for S1 to be essentially T over 2. That is the T on, the on time for the clock that's driving, or the pulse signal that's driving S1. So how would it look like? Well, if we sketch it here, and this is basically time, this is T over 2, and this is the cycle time T. So the signal S1, the clock or pulse 1 that's driving S1, will be on at time 0 equal to 5 volts, and it will stay on for T over 2 time. However, any signal in LT-SPICE or an actual circuit simulator has a finite rise and fall time. So it will not go from 0 to 5 volt in 0 time. Even if you put zeros as a minimum time that LT-SPICE compiler automatically set. Okay, so assume it takes, say, certain rise time to reach 5 volt, and also it takes specific finite amount of time to go from 5 volt to 0, say TR, another TR, okay? This is the duration. So now what is the problem with that? Well, let's look at pulse 2, or the clock that's driving the second switch S2. In this case, since we selected the duty cycle to be 0.5, T on of the second clock that's driving S2 should also be T over 2. Okay, so let me sketch it as dashes. So it will be on from T over 2 up to T. And the delay in this case, instead of being 0, when you set it in LT-SPICE, this delay parameter, it should be T over 2. Okay, now the problem is, as you can see, it's on S2, the signal, the clock that's driving S2 is on from T over 2 up to the end of the cycle T. But again, it will require a finite amount of time to rise from 0 to 5 volt, and also a finite amount of time to fall from 5 volt down to 0. So what is the problem? The problem is this triangle. During this interval, essentially, you will find that during this interval, which is 2 times the rise time, both S1 and S2 are on. If we assume here is the inductor, and this is essentially the capacitor in parallel with the resistor. So during this interval, both switches are on. So what will happen? You will have a huge short circuit, because these switches are, say, 10 milliohm each, 10 milliohm and 10 milliohm. So you can imagine VDC is 48 volts, so the short circuit current in this case will be 48 volt, or whatever VDC value, let's assume is 48 volts. divided by 20 milliohms, which is a very large amount of current. And specifically, if VDC is the battery voltage or something, you are shorting the battery, you can burn the battery, you can exceed its current rating. So we don't want this to happen. And by the way, this short circuit current, they quote also shoot through current, degrades the efficiency. So a lot of students, when they simulate a buck converter for the first time, theoretically they think they're going to achieve, according to their calculations, they will achieve an efficiency that approaches 95%, but they find the efficiency, say, 70% or even lower. The first reason that always 90% or 80% of students have is when they simulated, they have this overlap time. So how do we set the clock? Instead of setting the on time of the clock signal or pulse signal that's driving S1 as T/2, if we want the duty cycle to be 50%, we set T/2 minus 2 times the rise time. So the on time, as you can see here, for S1, the clock driving S1, is going to be 50% minus, or T/2 minus 2 times the rise and fall time, essentially. Or sorry, in this case, I'm assuming the fall time is basically equal to the rise time, and so essentially we subtract from T/2 2 times the TR. And similarly for S2, it will be delayed by half cycle, but again its on time for 50% duty will be essentially T/2 minus 2 times TR. And in this way, as you can see, as the third curve or the third graph, S1 turns off and right away S2 start turning on. And there is no overlap, and there is no this triangle or this interval where both switches are on to cause a huge short circuit current. Okay, and then this graph was for a duty cycle that's equal to 0.5. What about for other duty cycles? Well, for other duty cycles, again, the on time for S1, T1 for the clock that's driving the first switch, will be the duty cycle times the cycle time minus 2 times TR. So instead of T/2, it will be duty times TR. What about for the on time for the second clock that's driving S2? It will be 1 minus D times T minus 2 times TR. And note that for the clock that's driving the second switch, it has to be delayed. This delay parameter of the second clock should be equal to D times T. Okay, so that you can delay the clock by an amount of time equal to D times T, so that you have here the pulse for S1 and the pulse for S2, okay, and they repeat periodically. Now, in some cases, to enable something called zero voltage switching, which we will not discuss in this video, but to enable zero voltage switching, know that sometimes we need to add also extra blanking time or dead time. So in this case, say at 50%, so at 50%, what will happen is, as shown here, S1 will go to 0 and then will stay off for an amount of time equal to that time, and then at T/2, S2 start turning on, stays on until it goes to 0 again, and then we have the dead time again. Okay. Now to the required input decoupling capacitance in a buck converter. First of all, why we need an input decoupling capacitance? Well, if we think we're going to connect the transistor S1 and S2 in a buck converter, as well as the inductor, output decoupling capacitor, the load resistor, all these we're going to assemble into a board. So S1 is essentially a transistor, and its input is routed in the PCB plane or traces up to a header, or what we call banana jack, that looks like this. And this banana jack essentially receives the banana block cable from a measurement or what benchtop power supply, which we essentially use to characterize our buck converter. The banana cable introduces equivalent series resistance as well as equivalent series inductance. And the banana jack also introduced some kind of parasitic resistance and equivalent series inductance. And then the PCB traces or VN plane will introduce series resistance and series inductance. And then the packaging of the power MOSFET itself is going to, the pins in the package or the solder bumps in, if it's a GAN device, is going to introduce equivalent series resistance and inductance. And then we can add all these resistors together, and we call it the equivalent input resistance. And we can add all these inductances together, and we call it the equivalent input inductance. The sum of these resistors, by design, we can make it very, very small. We can make sure that the traces are of very small equivalent series resistance. This header or jack connector is basically of very small, has very large or wide diameter, so that it lowers the equivalent series resistance and so on. The problem that we have is in the equivalent inductance of the input Ln when we add, which is essentially the addition of all these inductances together. Why? We'll find that this parasitic inductance will introduce a huge overshoot here at the direct input of the transistor that causes extra voltage stress across the top switch of a buck converter S1. And that's why we need to connect a decoupling capacitor here. So let's study and estimate this noise. And by the way, if the input current of the buck converter was DC, IDC, so the voltage drop across these inductors will be zero, because the voltage drop across an inductor is proportional to the rate of a change in the current. And if it's DC, that rate of change is zero, so there will be no voltage change across the inductance. However, the problem, the input current of a buck converter is discontinuous. It periodically goes to zero every cycle. We studied the inductor current, and we know that it's a triangular waveform increasing during the first phase while S1 is on, and decreasing during S2 while S2 is on, and so on. And it has an average value equal to the current in the load. So what is the input current? Well, the input current is essentially the inductor current while S1 is on, which is this part. And when S2 is on, nothing is taken from the input, so essentially the input current becomes zero. And this waveform repeats, okay? So basically the input current is the inductor current while S1 is on, and then zero. And as you can see, it's discontinuous. Now, to study the effect of the parasitic inductance at the input trace from the input power supply or benchtop power supplies that we are using to test our buck converter, let's assume the inductance is very large, so that the peak-to-peak ripple of the inductor current is going to be zero. And essentially, the current is going to be a rectangle pulse as shown here, just for simplicity. And let's assume the input voltage, this voltage is 48 volts. And the input current, the inductor average, the load current is essential, which is the average value of the inductor current, is 20 ampere. And so the peak value of the input current is going to be rectangular pulse with an amplitude equal to 20 ampere. And it repeats. Now, the input current will not rise from 0 ampere to 20 ampere in zero time. It will have some finite time. Let's assume this time is about 20 nanoseconds. So it takes about 20 nanoseconds to for the input current to rise from 0 to 20 ampere, and another 20 nanoseconds to decrease from 20 ampere to 0 current. And let's assume the equivalent input inductance, the equivalent series input inductance is basically 20 nanohenry. First of all, if we look at the voltage drop across the 5 milliohm, it's basically a DC value equal to every time the current reaches 20, so it will be 20 times 5, which is 100, right? 100 millivolts. Which is not a big deal if we compare. VS is 48 volts, right? Now, let's focus on, so let's ignore the effect of the 5 milliohm for now. Let's focus on the effect or the voltage that will be generated across the 20 nanohenry. Excuse me. So, this is basically, as I mentioned, 20 nanosecond, and the time that's taken by the input current to move from 0 up to 20. To get the voltage that will be across the inductor is basically equal to Ln. It will be Ln times delta I n divided by delta t. Ln is equal to 20 nanohenry times delta I is 20 ampere and delta t is 20 nanosecond. So basically we have 20 volts. So we have 20 volts here, voltage drop, while the current is increasing. Remember, when the current is constant, the voltage drop across the inductor is 0. It's only why it's changing when inductances start to cause problem. When current is changing in an inductor causes voltage drop or voltage variation. So the voltage across, now the input voltage here, while the current is increasing, will be the 48 minus 20, which is 28 volts. Okay, so it will look like this as the inductor current is increasing. The voltage essentially at the input of the buck at S1 is basically 28 volt. Now, while the current is decreasing, you essentially the polarity of the voltage will just be reversed. Instead of having positive polarity on the right side of the 20 nano or left side of the 20 nanohenry, it will be on the right side of the 20 nanohenry, and you will get here 20 volts. So essentially the voltage here will be the 48 volts plus 20, which is 68 volts, and you find suddenly the voltage jumps to 68 volts, and that's what you'll observe in simulations. We'll have a sudden drop and a sudden peak. While the drop might not be that of a big deal, the issue is in this overshoot, because this overshoot will appear across S1, and S1 will see the entire 68. So instead of selecting a switch S1 that can handle a maximum voltage of say 48 volts or a little bit higher usually, say in this case 48 volt because the input is 48 volt, we have to select a more expensive switch or a bigger switch that can handle up to 68 volt maximum voltage. Okay, so to solve that, we use an input decoupling capacitor right beside the top switch in a buck converter. And the whole idea here is if we apply KCL at this node for the DC component of IN, again this is a periodic signal, it has a DC component and AC harmonic. The DC component of the input is basically the duty cycle times I out, as we discussed before. And this DC component will see the capacitor as open circuit, so it will only flow in the parasitic inductances and the equivalent series resistance of the input line, or the connection to the input power supply VS, the 48 volts. While as for the harmonics, the harmonic components of the input current will see this branch in parallel with this branch. If we assume Cn to be very large in value, This branch will act as a short circuit at the fundamental as well as the harmonics of the switching frequency we are using in the buck converter. So essentially Cn will shunt all of the harmonics of this input current, and so the current in the capacitor is the harmonic components of this waveform, which is essentially In, the input current, but without its DC component Di out. So all we need to do to get the current in the capacitor to shift this waveform by this value downward. So going back to the actual waveform, this was just a simplified waveform for the input current to, or exaggerated waveform in order to be able to give you how the actual input voltage to the buck converter would look like. We can call this V1. So this will be V1. Now, now if we, as I mentioned before, the input current is basically the inductor current while S1 is on. So it looks like this, partial trapezoid. And the current in the capacitor, we just need to shift it downward by an amount equal to the average component of this current, which is D times I out. So if we have 0 and subtract Di out from it, it becomes minus Di out. And similarly, as you remember, this average essentially of the inductor current is I out. So this part of the trapezoid is essentially I out. So if we subtract Di out from it, it will be 1 minus D times I out. And then if we calculate the RMS value of this waveform, we'll find it given by this simple expression. Okay, and all we need to do now, after we calculated the RMS current that's flowing into the input decoupling capacitor that we are going to use, when we select an input decoupling capacitor, we should select it such that its RMS current rating is larger than the value that we need in our design. All I care about here is calculations are easy to do for the required value for the input decoupling capacitor, but what I care more about is that when you design a printed circuit board for a buck converter or any other converter, you would need to add decoupling as close as possible to the switch that connects to the input, to the power converter. And the reason is because the cable, the banana connector, as well as the PCB planes and any package parasitics of your transistors will introduce parasitics that you need to take care of. And by the way, if the transistor is not solder bump, it has a finite package, and this represents the bond wires, and the capacitor will be effectively here, and you will have some kind of noise here, but it should be smaller given that the voltage variation here is L proportional to this L, the smaller L of the bond wires of the power FET, di dt.